noon, I screw up in the morning and then I correct things, and then for you guys, it's a little bit better. Just a little bit better, not much. So recording, nothing, so it's okay. Okay, so what we're gonna try to do today, we're gonna keep talking about Doppler effect, but we're gonna talk about a specific situation of Doppler effect that is basically this situation. We have an echo, so we have a source that is sending a wave. It hits a target, and from that target, the sound wave bounces off to the source, and the source receives it as an echo. And when you have that situation, there's a double shift. There's a shift when it goes up to the target. There's another shift when it comes back to the source, and that's basically how echolocation works. And the main objective of echolocation is to find out how far the target is and how fast the target is moving. So that's more or less what we're gonna try to do. So let me share this thing. Okay. So that's basically what we're gonna try to do. We're trying to find out and describe what happens when we have a case of echolocation. And we have a source. In this case, can be our bat, and he's chasing a moth. And basically what we're gonna have is that and there's a chase, right? So this guy is moving in this direction, this guy is moving in the same direction. And basically what we're gonna have is that it's gonna meet a sound wave. There's gonna be a shift in frequency on the way to the target, and then on the way back, because the source is still moving and the server is still moving, there's going to be a second shift on the way back. Okay, so here's the thing that we need to figure out. There's a shift in frequency. When the sound travels to the target, and when the sound bounces off back to the source. Okay, so the way you solve these kind of problems is basically dividing the Doppler effect in two parts. One when it goes up to the target, and then the second part when it bounces off. Okay, so the first part the sound travels from the source, in this case the bat, to the observer. And there's a shift of frequency. And I'm going to call this shift of frequency F0 prime, F naught prime. Okay, now when the sound bounces off, this frequency is going to be the frequency that is bouncing off. And my target, the moth, is going to be my source, and the bat that is receiving the echo is going to be my observer. So kind of switch roles. Okay, so the shifted frequency is my new source frequency. The mod becomes the source, and the bat is a new observer. And I need to apply Doppler effect once again. Okay, make sense? Yeah. Okay, I thought you were saying like slow down.
No.
Yeah, makes sense. Ish. Okay, so we'll do a really quick example. And let's assume that we have this case. We have a bat chasing a moth. So we have, I'm gonna draw it like this because I'm getting tired of drawing bats. Okay, and I'm gonna say that this bird is emitting some kind of echolocation. I don't know if birds have echolocation. I don't know any biology major. So I'm gonna say that it's emitting a frequency of 30 kilohertz. And I'm gonna say that originally this is traveling at 50 meters per second. And there's a chase here. The moth is traveling at 20 meters per second. And this is air, and I'm gonna say that the velocity of air is 340 meters per second. Okay, so first thing I'm gonna do is I'm gonna try to calculate what is the frequency that the moth is perceiving. Okay, so I'm gonna calculate, so the frequency that the moth okay, so I'm gonna apply this equation. Okay, so this F naught prime, this is gonna be the frequency that the moth perceives. VO will be the velocity of the moth, VS will be the velocity of the bird or bat, and Fs is the velocity of the source. Okay, the plus and minus depending is, I remember it's gonna depend whether there's this relative motion between the two of them. So try to find out what is this equation without looking at your notes. Okay, so remember, in this case, to find whether we have plus or minus in the numerator, we're going to assume that the source is static, and then depending if it's getting towards, away from the source or towards the source, the frequency has to go up and down. To find the denominator, the sign of the denominator, I'm going to assume that the moth, the velocity of the server is 0. And then depending if the source is getting closer to the server or away, the frequency has to go up and down. So try to find this equation without looking at the notes, Mason. Try to do it without looking at the notes. We'll if you get started, you can look at the notes, but let's try first without looking at the notes. Yeah, I'm gonna solve this part. So I'm gonna try to find out here in the denominator if I should have a plus or minus. So to do that, I'm gonna assume that the observer, this moth, the velocity is zero, so it's static. And if this is zero, the bat is getting closer to the moth. Okay, so that means that the frequency has to go up. So I will need a negative sign in the denominator. Now for the numerator, I'm going to do the same thing. I'm going to assume that the velocity of the source is zero. So this is static. And then this thing is moving away. So if the move is moving away, the frequency has to go down. So this will be also a negative sign. So that would be my equation. And then I can substitute some values. So I'm going to find 340 minus 20 over 340 minus 50 times 30 kilohertz. And I got 33.1 kilohertz. Yep. Okay, notice that the shift in frequency, the increase in frequency is 3.1 kilohertz. So I'm going to call here just a little note. Delta F is 3.1 kilohertz. Okay, now this frequency over here, this 33.1 kilohertz, is the frequency that is bouncing off the moth. Okay, so when the sound comes back, when I have that echo, then I'm going to assume that the moth is going to be my new source. Okay, so now the frequency of the source is going to be F naught prime. And the bat is going to be the observer. And I'm going to use the same equation. Okay, so now remember, now the observer is going to be the bat, the source is going to be the moth. Okay, so because the rule changed, now the signs are going to be a little bit different. Okay, so try to find again what will be the signs. How do we simplify that equation with the new rules? Okay. So the echo, the frequency of the echo. So again, I'm gonna assume that my observer is static. So this is static. The source is moving away, so the frequency has to go down. So here I will have V plus Ds. Now I'm gonna assume that the source is static and the source is getting closer, so the frequency has to go up. So here I will have V plus V naught. So here I will have 340 plus 50, 340 plus 20. Times 33.1 kilohertz. Yeah. Okay. Any question? If I calculate delta F, so the difference between 33.1 kilohertz and the 35.75, this is delta F. This is going to be 2.75 kilohertz. So not exactly the same. Okay, makes sense? Okay, we're gonna do another problem, similar. We're gonna do a problem that's a little bit easier. I'm not gonna let you guys do it on your own. And let's go. So I have a radar. And the radar is looking at a cloud with rain. Okay, the cloud is at, I'm gonna say that it's at 30 kilometers away from the radar. And this cloud is moving at a speed of 10 meters per second away from the radar. Okay, the frequency of the radar, I'm gonna say that is 500 kilohertz. Okay, so a couple of things. I want to know one. So you can imagine that the radar is sending kind of like pings, kind of like a little burst of the signal. So it sends a ping and it waits for the ping to comes back, and then it looks at the shifted frequency, and it keeps doing that over and over. So I want to know how long it takes for each one of these pings to get back. So what will be how long does it take for the echo to come through? And then I want to know frequency at the cloud. And also calculate the delta, the shifted frequency, delta F. And 3, the echo frequency. At the radar. And also I want to calculate delta F. Obviously the radar is static, it's not moving. And so the problem is a little bit simpler than what we did before. Okay, makes sense? Okay, so I'll give you guys a couple of minutes to do it, and then we'll do it together. Yeah.
Are we still using 340?
Say that again?
Are we still using 340?
Oh, yeah. Let's assume that the speed of sound is 340. So if the cloud is moving away, the frequency goes down or up. So go down, right? But here you are getting a factor of larger than 1. Or this will have to multiply by 500. So you're going to get a frequency, higher. Now, double check because your source is the one that's studying. Because the source is the one that's checking. Yeah, so the sources are using T equals T. You could get that equation for it's just a solve it. Now, when the weight goes down, then this is going to be source. There is something there. So, you're gonna have the frequency going down one way and going up the other. The one that we're using before. You can see this one. And then simplify that equation to get the one that you. I think most of you got the first part correct. Well, let's do the first. Let's do the first part. How long does it take for the echo to come back? So, so you send the signal, the ping signal, and it's just a sound wave. So it's going to be traveling at 340 meters per second. It travels 30 kilometers to the cloud, and then 30 kilometers back to the cloud, from the cloud to the echo. And that's going to be the round trip of that signal. So the velocity is going to be distance over time. So time will be distance divided by the velocity. So the distance is going to be the 60 kilometers. So 60 times 10 to the 3 meters. And the velocity is going to be the 340 meters per second. So I have 176.47 seconds. Okay, so almost 3 minutes for that for the round trip. Okay, now I'm gonna do part number 2. I want to find out what is the frequency of the cloud. So here I'm gonna assume that the velocity of the source is 0. So my Doppler effect equation is going to be B over, no, here I'm going to have V minus V naught over V times the velocity of the source. Now, how do I know that I have a negative sign here? Because the cloud is moving away from the radar, so the frequency has to go down. So this factor has to be less than 1. So I will have 340 minus 10 over 340 times the 500 kilohertz. And this will give me what, 485.3 kilohertz? That's what you guys got? Okay. And if I want to calculate delta F, so that would be the 500 kilohertz minus 485.3. I get what, 14.7. Okay. Now I'm going to do the same for the second part. Now, in this case, the observer, the velocity of the observer is going to be 0. And the velocity of the source is going to be 10 meters per second away from the observer. Okay, so I'm going to have my shift in frequency. So this will be V. There's no the velocity has the observer has 0 velocity, and here I'm going to have V plus Vs times the frequency. Okay, again, the source is moving away from the observer, so the frequency has to go down, so I will have to have this positive. So here I will have 340 over 340 plus 10 times 485.3. And let me double check. And I get 471.43 hertz. Everybody got that? And if I want to calculate delta F, I will get 13.86 hertz. Kilohertz. Yeah, makes sense. Any questions so far? Okay. Now, usually when you're doing, when you're using Doppler effect, the way you actually do it in real life is that you know your frequency, you may know how far the cloud is, but you don't know what is the velocity of the cloud. That's what you want to find out. You may have the shifting frequency. That's what you are detecting. That's what you're measuring. And from that measurement, what you want to find out is the shifting frequency. So we'll do one problem. And let's say that you have a Doppler effect measurement for your blood. I don't know how you call those things, but you are measuring the speed of red cells in the body. So you have your Doppler effect thingy. You are emitting a frequency of 500 megahertz. And the frequency of the echo is 5.3 megahertz. Okay, and you want to know how fast these red cells are moving. I'm going to say that is 5.05. That's the shift in frequency. Instead of 5.3, 5.05. Okay, so this is a long problem. There's a little bit of algebra here. You need to apply uh, Doppler effect twice without knowing the velocity, okay? One thing that we can find out just by looking at those numbers that what would be the direction of the cells? Are the cells moving towards the radar or moving away from the radar? Away?
Towards it?
It's moving towards the radar. And we know that it's moving towards because the frequency is going up. Even if it's a little bit, but it's moving up. So it has to go towards. Okay, that's one thing. The other thing, the other piece of information that we know is the speed of sound in the blood, and I'm gonna say that this is gonna be 1600 meters per second. Okay, give it a try. I'll give you 5-10 minutes, and then we'll do it together. Okay. Yes.
Can you move it back?
Oh, sorry. Is the frequency that the radar is receiving. It's the frequency of the echo. Try to keep track of what is your source, what is your server, especially when it goes back. Yeah, Gary, so that 5.05, that's the wave bouncing off the cells and coming back.
Oh.
Okay?
Okay.
They will need to subtract this from this.
Subtract by the
Okay, so so again, this is going to be kind of like a round trip. Okay, so we need to apply the Doppler effect twice. So I'm going to go from the radar to the cells. And I'm going to assume that the velocity of the source is 0 and the velocity of the cells, this is an unknown, okay? And actually, I don't even know what is the shifting frequency, but I'm gonna grab the equation. So I'm gonna have this shifting frequency that is gonna call FL prime. The source is 0. So I'm gonna have this equation over here. Okay, I know that the cells are moving towards the radar, so the frequency is going to increase, and I'm going to have this factor bigger than 1. I don't know what is this frequency. I don't know what is I don't know what is this frequency. Sorry, I don't know what is the frequency that the cells are receiving. Okay, but whatever it is going to have to be defined by this equation. Okay, now I'm going to do the second case, and it's from the cells to the radar. This is the echo signal. This is the one that is bouncing off the cells. So I'm going to have F naught. Now my source is the one that is moving. My object is 0. My observer is 0. And because I'm moving closer, this is going to be negative. And this is going to be FO prime. This is the frequency that is bouncing off the cells. Now, I know that this is going to be the 5.05 megahertz. And instead of writing this FO prime, I'm going to write this equation that I have here. So I'm going to have this 1. This is going to be 2. And I'm just going to substitute equation 1 into 2. Okay? So I'm going to end up with this. And some of them are going to cancel. So I'm going to have B over B minus BS. And here I'm going to have, no, sorry, B plus B naught over B times Fs. I know it looks kind of complicated, but this is going to be my 5 megahertz. This is a 505 megahertz. Now, it seems that I have two variables, B naught and BS, but these represent the same object. These represent the cells. So this will be B plus the velocity of the cell. So I'm going to B sub B, and this is going to be minus B sub B. Okay, and then this is the one that I need to solve. It's a big equation, and it's going to be a lot of algebra. So I'm going to try to do it slowly. Okay. So I'm going to have 5 divided by 5. That's going to be B. Okay, this is going to be 1.01. This is plus, and this is going to be minus. I'm going to multiply the denominator on both sides of the equation. That's going to be equals to B plus B. And then I'm going to expand this factor. Okay, and then what I'm going to try to do is isolate the variable. So I'm going to, everything that belongs to the velocity of the cells, B sub B, I'm going to put it on the left side. Everything else I'm going to put it on the right side. So this is going to be subtracting. So I'm going to have minus BB minus 1.01 BB. This one is going to subtract also on the other side. So it's going to be V minus 1.01 B. So now here I can factor out the velocity of the cell. So this will be, well, I'm going to add them together. This will be 2.01 BV. And here I'm going to have negative 0.01 B. And from there I can solve for over the velocity of the cell. That will be 0.01 v over 2.01. Okay, and I think that should give me 8. Gives me 7.96 units per second. Okay, now this is a pain in the butt. This is actually a very complicated problem. Now we can do it a little bit easier, and if the velocity of your object, if the velocity of the target, whatever is moving, is very small, so if the velocity of the object is much smaller than the velocity of sound of the medium, and if you're looking at this shift in frequency, then you can make an approximation, and you can say that the shift in frequency is going to be plus minus 2 the velocity of the source over times the velocity of the object over the velocity of the wave. Okay, so delta F will be that difference between the frequency that you send and the frequency that you receive. And this is going to be the frequency of the source. This is the velocity of the object, and this is the velocity of the wave that you are receiving. Plus minus is going to depend whether you have an increase in frequency or a decrease in frequency. Okay, so let's do with the problem that we have right now. So I have Fs to be 5 megahertz, and the frequency of the echo is 5.05 megahertz. So delta F is going to be 0.05 megahertz. Okay, so this is going to be over here. So I'm going to have 0.005. That's going to be equals to 2. The frequency of the source is going to be 5 megahertz. V naught is the one that I want to find out, and V is the velocity of the sound in the medium. Okay, so from there I can find the velocity of the object. And this will be 8 meters per second. Okay, it's not exactly the same. This is an approximation. But if your velocities are very small to compare to the velocity of the sound, it's a very good approximation. And you can save yourself a lot of algebra. Okay? Make sense? Any questions? Okay, Wednesday we're gonna keep doing some problems involving Doppler effect. And that's it. Have a good day and see you guys on Wednesday.
Because we didn't.